Hi, welcome. So, have you ever found it difficult to create a retaining wall structure with the stiffener on it? Did you find it time consuming, especially if you are looking for creating such models for repetitive multiple projects? If it is so, then you are on the right video. So, in this video, we will see how we can create the automated template for generating multiple complex retaining wall structures in STAAD with the help of AI and the Python code. So this is an example of how the power of OpenStaad Python and its library can be coupled with AI to create multiple automation tools that are not only scalable but can also address complex modeling challenges that would be extremely difficult and time consuming to handle it manually. So this particular module or the application is designed for retaining wall modeling, including complex curve-shaped retaining walls subjected to compression, soil spring behavior, lateral earth pressure, and the hydrodynamic pressure. Such automation can be particularly useful for design and analysis of flood mitigating structures. Now, this application allows users to create both the buttress and the counterfort retaining walls in either straight or the curved configurations, while automating much of the geometry creation and the loading and the modeling process. The key advantage is that what would traditionally require extensive manual modeling and repetitive effort can be transformed into a scalable, intelligent, and highly automated workflow using OpenStaad Python and AI. So this Python code was developed with the help of large language model or LLM. For this application, I used Claude Opus through Microsoft Copilot, where the Claude LLM is already integrated. I had initially instructed the AI to create a module for modeling a retaining wall subjected to active earth pressure and the hydrostatic pressure. The challenges becomes much more greater while the profile is curved. Essentially, there are two key challenges. First is the geometry itself, that is the curved geometry. Now, creating and meshing a curved retaining wall is far more tedious than the straight wall. Secondly, the defining the soil spring behavior. Essentially, the soil behaves as a compression-only spring. Now, this soil reaction acts normal to the curved surface, so its direction continuously changes. Since that defines the compression-only spring in the global direction, a conventional spring definition cannot directly represent this behavior. Therefore, we need to have some alternative approach to define the spring action correctly along the curve profile. So this is where AI, Python, and the OpenStaad library becomes very powerful. AI helps to generate the Python automation to create the geometry mesh connectivity and the appropriate orientation of the support condition seamlessly, turning a highly complex manual modeling task into an automated workflow. So we will see forward how we have created this application. The entire Python code was created with the help of LLM model. We have used standard Python libraries such as NumPy, Math, and few system native libraries. Along with this, we have also used the OpenStaad Python package, which is recently developed and integrated with STAAD.Pro 2020-2026. We have also used two additional libraries like PySlide and PyVista. PySlide is used to create the graphical user interface like Windows button, menus, and other desktop application elements. On the other hand, PyVista provides a high-level interface for visualization, such as 3D meshing, scientific data, and geometric shapes. As you can see, the code is quite intensive, more than 1,000 lines. Obviously, this entire refined code was not generated by a single prompt. I had to walk through perhaps 9 or 10 different set of prompts continuously instructing AI model, reviewing the stat model it generated, identifying what is needed to be changed, and refining the logic. This is where engineering judgment becomes more important. The AI can generate the code, but you still need to review both the code and the resulting stat model and make sure the model represents the actual engineering situation correctly. I would consider myself an average Python programmer, not a professional developer. I do understand Python and the basic knowledge, but I'm not an expert. So with that level of knowledge, I was still able to use AI to develop a Python application for this complexity, something that could otherwise have taken several days or even more than a week to build this manually. So let's run this application. You can see here that the application has generated a very clean and interactive graphical user interface. We have different sections for geometry, thickness, supports, loading, and other relevant inputs. So let's go through one by one. First, we have the mesh size. I'm going to keep the default value for now. If you need a coarser mesh, you can increase the mesh size. However, if you need a finer mesh, you can reduce the number. The default values, however, is reasonably good for this demonstration. Next, we can control the geometry. For example, we can define the curved radius. If you don't want the curvature, you can simply leave it as a default value with the zero curvature, and the wall will remain straight. For example, let's define the radius of curvature as a 60 meter. All the dimensions here are in meter and thus follow the SI system. We can also define the direction of the curvature. If I change the direction and update the preview, you can see the wall curves in the opposite direction like this. Now we can also control the placement of the counterforts or the stiffeners. They can be positioned either on the heel or the toe side. You can also define these positions manually. For example, you can specify the required spacing and the program will automatically place the counterfort at those spaced location. So let's make the wall slightly longer, like 45 meters, and keep the other parameters at their default values. And I'll keep the counterfort on the heel side. Now, when I update the preview, you can immediately see the resulting geometry. This is one of the advantage of having the interactive GUI. You can visually understand how the geometry is being generated and also get a quick idea of how the hydrostatic loading is distributed along the wall. Next, let's move to the thickness section. Here we can define the thickness at a different location. These are the default values. For example, I can change the bottom thickness from like 0.5 meter to 0.85 meter, assuming that we require a significant tapered thickness. You can modify these values according to your engineering requirements. The current GUI doesn't graphically display the tapering in this preview, although that could certainly be added as a further refinement in the code. However, we are able to generate the actual STAAD model with the tapered geometry. So next we come to the support. Now this is probably the most important and technically challenging part of the entire workflow. You could simply model the base as a fixed support, which would make things much more straightforward. But if we want more realistic representation, we need to consider the actual soil behavior. So here we assume that the base is resting on the soil medium, which is not infinitely stiff. So we can define the soil subgrade modelers and the program would automatically model the base as a plate mat, which has the specified soil stiffness and the compression only behavior. However, modeling the soil structure interaction along the wall is much more challenging, particularly because of the curved profile of the wall. One option would be to model the vertical wall as a compression only plate mat, but with a curved profile, defining the compression only behavior becomes very difficult. The reason being, the compression only behavior acts only along the global direction. So we have used an alternative approach. We create compression only dummy members along the wall. These members essentially act like a compression only springs, allowing the wall to transfer compression to the soil while avoiding the tension. We also define an appropriate dummy member length to represent the required compression behavior. This allows us to simulate the soil structure interaction in a very practical way, even for a curved wall profile. Now, for the lateral soil structure interaction, we define the soil subgrade modulus as input, representing the stiffness of the soil acting against the wall. Now, the key question then is how we define or determine the stiffness of these compression only members. So the program converts the lateral soil subgrade modulus into an equivalent member stiffness. So these members effectively behave like the soil springs. The advantage of using this member is that we can orient them in any desired direction. Since the wall is curved, we don't want all the springs aligned along the global axis. Instead, they are oriented along the radial direction, which is can be represented as a local axis. That is the normal to the wall surface. The local direction therefore changes along the curved wall while remaining perpendicular to the wall. The local direction therefore changes with respect to the global axis system while remaining perpendicular to the wall. Based on the inputs provided, the program calculates the equivalent cross-section properties required for these members and automatically assigns them to the wall. Now we can also define the soil side, whether the soil is acting towards the left or the right side of the wall. Based on this selection, the compression only members are automatically positioned and oriented in the appropriate direction and connected to the fixed support. So now let's move to the loading part. Here we can define the self-weight and the hydrostatic water pressure. We can also activate the lateral earth pressure using this checkbox. Once I activate it, you can see the change in the visualization. The blue color represents the water pressure while the brown color represents the soil pressure. Now, because of this curved wall, we can also control the direction in which the loads are applied. We can choose either the global or the local direction. Now, for this model, it is more appropriate to use the local direction, so the load remains normal to the curved wall. Now, the important part is since this is a non-linear problem due to the compression on the spring, we cannot simply use the conventional load combination. Instead, we use the repeat load feature. Now, this repeat load feature instead actually creates a primary load case in which different load effects are combined and solved together. This is very important because the nonlinear response cannot be obtained simply by algebraically adding the responses from the individual primary load cases. These are the default load factors. You can change as per your need. You can also choose whether we want application to generate the required static analysis output and the printouts like this. Once every inputs are provided, you can click on this generate model. Now I have already opened a blank stat file. Now let's generate the stat model from here. And here we have the completed model. Now let's zoom in and look at the spring support. You can see these compression only members connected to the fixed support. These members effectively represent the compression only soil behavior. Now based on all the inputs we provided, the application has automatically generated the complete stat model, including the curved wall, counterforts, tapered thickness, support, and the soil interaction. You can also see the tapered wall section at the base. Now let's look at the loading. We have the self-weight and the hydrostatic water pressure and the lateral earth pressure. Now this application has already grouped the relevant effect through the repeat load for the combined effect. Now let's run the analysis. Here you can see the resulting plate stress output. And this is where the application can be extended further. For example, you can extract the required plate forces and the plate stress and other analysis outputs and use them for your design calculations.